Hydrogen and helium are the two most abundant elements in the universe, making up the vast majority of all matter. Yet, when we look at Earth, these elements are surprisingly scarce. This paradox raises intriguing questions about the processes that shaped our planet and its atmosphere. While stars and interstellar clouds are rich in hydrogen and helium, Earth's composition is dominated by heavier elements like oxygen, silicon, and iron. Understanding why these light elements are so rare here, despite their cosmic prevalence, offers insight into the history of our solar system and the unique conditions that led to the formation of our world. Hydrogen and helium are the two most abundant elements in the universe, and their origins trace back to the very beginning of cosmic history. Shortly after the Big Bang, the universe was a hot, dense soup of particles. As it expanded and cooled, conditions became favorable for protons and neutrons to combine, forming the nuclei of hydrogen and helium. This process, known as primordial nucleosynthesis, occurred within the first few minutes after the Big Bang. The vast majority of matter created during this period was hydrogen, with helium making up most of the remainder. These elements formed the foundational building blocks for stars, galaxies, and ultimately, all visible matter in the cosmos. Their initial prevalence set the stage for the chemical evolution of the universe. In the earliest moments after the Big Bang, the universe was a hot, dense soup of fundamental particles. As it expanded and cooled, protons and neutrons began to combine, forming the nuclei of hydrogen, helium, and trace amounts of lithium. This process, known as primordial nucleosynthesis, occurred within the first few minutes of cosmic history. The vast majority of hydrogen and helium present today originated during this period. Over billions of years, stars have played a crucial role in shaping the distribution of these elements. Through nuclear fusion, stars convert hydrogen into helium and, in rare cases, produce lithium. When stars die, they disperse these elements into space, enriching the interstellar medium and influencing the chemical makeup of future generations of stars and planets. Earth's composition is unique when compared to the broader universe. While hydrogen and helium are the most abundant elements in stars and interstellar space, they are relatively scarce on our planet. This is largely because Earth's gravity is not strong enough to retain these light gases, which tend to escape into space. However, hydrogen is still present on Earth, most notably as a component of water, where each molecule contains two hydrogen atoms bonded to oxygen. Hydrogen can also be found in certain minerals, contributing to their chemical structure. In contrast, helium is even rarer, typically found only in trace amounts within natural gas deposits. The abundance of heavier elements, such as oxygen, silicon, and iron, shapes the Earth's crust and interior, setting our planet apart from the gaseous giants and the Sun. Billions of years ago, our solar system began as a vast, rotating cloud of gas and dust known as the protoplanetary disk. Within this disk, gravity caused material to clump together, gradually forming the Sun at its center and the planets in orbit around it. Earth and its neighboring planets emerged from the heavier elements and rocky debris that remained after most of the hydrogen and helium were swept away by the young Sun's intense solar wind. While gas giants like Jupiter and Saturn managed to retain large amounts of hydrogen and helium, the inner planets lost these light gases due to their weaker gravity and proximity to the Sun. As a result, Earth became a rocky planet, composed primarily of silicates and metals. This process set the stage for the diverse worlds we see in our solar system today, each shaped by the unique distribution and fate of cosmic material. Earth's gravity, while sufficient to hold onto heavier gases like nitrogen and oxygen, is not strong enough to retain the lightest elements such as hydrogen and helium over long periods. These light gases move at high speeds due to their low molecular mass, making it easier for them to escape Earth's gravitational pull. Additionally, Earth's close proximity to the Sun means it is exposed to intense solar radiation, which heats the atmosphere and further accelerates the loss of these gases. In contrast, the gas giants are much farther from the Sun, experiencing less solar heating, and possess significantly stronger gravity due to their massive size. This combination allows them to hold onto vast amounts of hydrogen and helium, forming thick, gaseous atmospheres. As a result, Earth's atmosphere is composed mostly of heavier gases, while the gas giants remain rich in the lightest elements. Helium is distinguished among the noble gases by its remarkable stability and lack of chemical reactivity. Unlike most elements, helium atoms have a complete outer electron shell, which prevents them from forming bonds with other atoms. This inertness means helium does not easily combine with other substances, making it chemically isolated in nature. As a result, helium is rarely found in compounds and is typically present only in its pure, gaseous form. Its inability to bond also contributes to its scarcity on Earth, since it can escape into space rather than being trapped in minerals or the atmosphere. These unique properties make helium both fascinating and challenging to obtain. Helium on Earth is primarily formed through the process of radioactive decay. Deep within the planet's crust, certain heavy elements, such as uranium and thorium, undergo decay and emit alpha particles. These alpha particles are essentially helium nuclei, consisting of 2 protons and 2 neutrons. Over time, as these particles capture electrons, they become stable helium atoms. The newly formed helium can migrate through porous rock, but in some cases, it becomes trapped in underground reservoirs. This natural accumulation is why significant amounts of helium are found in certain gas fields, often alongside natural gas deposits. Helium is a unique element that gradually escapes into space due to its light atomic structure and the inability of Earth's gravity to retain it indefinitely. This continual loss makes the accumulation of helium reserves a significant challenge. Helium is indispensable in various fields, including medical imaging, scientific research, and aerospace engineering, owing to its inertness and extremely low boiling point. Most helium is extracted from natural gas deposits, where it has accumulated over millions of years from the radioactive decay of heavier elements. The extraction process involves separating helium from other gases, which requires specialized equipment and considerable energy. Because natural sources are limited and replenishment is slow, managing and conserving helium reserves is crucial for sustaining its critical applications. Hydrogen is more abundant than helium on Earth, primarily because of its unique chemical properties. Unlike helium, which is a noble gas and rarely forms compounds, hydrogen readily bonds with other elements. One of the most significant examples is its combination with oxygen to create water, a substance that covers much of our planet. This ability to form stable compounds means hydrogen is found in a wide variety of natural materials, from water to organic molecules. In contrast, helium remains mostly isolated and escapes into the atmosphere due to its inert nature. As a result, hydrogen's versatility and prevalence in essential compounds make it far more common on Earth than helium. In summary, the story of hydrogen and helium is shaped by the vast processes of cosmic evolution and planetary formation. While these elements are the most abundant in the universe, their physical properties, such as low atomic mass and high volatility, make them difficult to retain on Earth. During the early stages of our planet's formation, intense solar winds and the lack of a strong gravitational pull allowed most hydrogen and helium to escape into space. This interplay between cosmic origins and planetary conditions explains why, despite their universal prevalence, hydrogen and helium are surprisingly rare in Earth's atmosphere and crust. Their scarcity here serves as a reminder of the dynamic forces that have shaped our planet since its birth.